Okay, and welcome to the next video where we're going to look at natural logarithms, which is a special type of logarithm which deals especially with e to the power of x. Again, very important type of logarithm. So, we saw in the last video that all log graphs before transformation have this shape, okay? And they all come from reflecting the exponential in the line y equals x. Now, ln x, we should remember from the previous video, ln x is log base e to the x. Now, that is a reflection of the e to the x graph, which if you remember from the exponential video, e to the x is a special type of exponential where if you differentiate it you get the original graph. You can use the fact that logarithms are inverse of exponentials to solve equations involving powers and logarithms. So one of the most powerful examples of this is if you've got e to the power of ln x, or ln to the power ln with e to the x, then what happens is the e and the ln undo each other because they're inverse functions. And if you've got an inverse function and you apply the original function or vice versa, they undo each other's properties and you're left with the original value. So that's quite an important thing to remember. So let's get into solving these equations and seeing what kind of skills we need to solve them. Most important thing is to remember before we start solving them that these are still exponentials and these are still logs. There's no special technique really. Right, e to the power of x equals 8. That's an exponential form. So what I'm going to do is, to solve that, I'm going to drop the e as the base, I'm going to write in log form, put the 8 here, equals x. We don't normally write log base e, so remember log base e is the same as ln, so the answer is x equals ln 8. And that's it. Yeah, all we've done is what we've done in the previous videos. Part B, 2 ln x equals 12. There's two ways of doing this. I'm just going to divide through both sides by 2. So I get ln x equals 6. Now, don't panic with this. Ln x is just log base e to the x. Okay? And if that's the case, let's get into exponential form. And in exponential form, this e, which was the base, must have originally been the base of the exponential. 6 would have been the power, and x would have been the value. Okay? So the solution is e to the power of 6. And these are what we call exact form solutions, okay? Either in terms of ln or e to the power or something. We do not convert them to decimals to get exact form. Okay. Question 2. Part A. 2 to the power of e to the 2x plus 4 equals 12. I've got to solve that. Well, again, I've got 2 in front of the e. Let's divide through. You get 6. Now I've got e to the power of something equals 6. Now again, this is exponential form. I'm going to convert into log form. So I'm going to get log base e 6 must be equal to 2x plus 4. Yeah, so you can convert from exponential to log in that way. This number becomes the base, the 6 goes in the side, the 2x plus 4 goes in the side. Log e to the 6, that's ln 6. And we want the answer in exact form. I'm just going to rearrange. So make x a subject, ln x minus 4 times by half. Okay, or half ln 6 minus 4. Minus 4 and divide by 2. Part B, 3 ln x minus 4 equals 8. I want x again, so I'm going to add 4 and divide by 3. So when I add 4 I get 12, divide by 3 I get 4. I've got to solve that. Now ln x equals 4, that must have meant we've got log base e x equals 4. That means originally, if I put that in exponential form, that must have meant e to the 4 equals x. Okay, so again I'm going from log form to exponential. Final one, question 2. We've got e to the power of 2x plus 5e to the x equals 14. Now, I cannot apply the same sort of skills here. So what I'm going to do is I'm going to just make everything equal to 0 instead of 14. Now again, if we remember the trick from the previous video, anything to the power of 2x can be rewritten as this. An exponential quadratic. Yeah, got the quadratic, something squared plus a number something minus another number. So I can factorise this. E to the x plus 7, e to the x minus 2. So you get e to the x equals 7 minus 7, or e to the x equals 2. Now, the problem is with this question, if you look at the e to the x graph, there's no value of x which gives you 7, minus 7. Okay, so there's no value of x which you put it in, which makes e to the power of x equal to minus 7. So e to the power of x equals minus 7, that actually gives you no answers. Okay? But e to the power of x equals 2, that can give you a solution. And again, you just need to get into log form, and a bit of work, you get x equals ln2. Right. Question 3. Final question of the sheet. The number of atoms of a radioactive particle, mathsium 96, at time t hours is given by this formula, where n is the initial number of atoms and k equals 1.3 times 10 to the minus 2. Sketch a graph of atoms, number of atoms against t, showing n0, half n0 and the half-life t. So remember, for a sketch we need a pencil and ruler. Okay. Now we've got to draw a graph of number of atoms against time. 0 here. Should not have negative time. What about that? So it's going to look like that. Now, if we look at the type of graph that we've got here, we've got e to the minus something t. And if you remember the video when we looked at exponentials, then it's going to be a decay graph. And those of you that study physics will recognise it anyway. So what happens is we've got an initial amount of atoms, and that initial number is what we call n0. Okay, so at time t equals 0 we've got a certain number, and the graph should exhibit this sort of behaviour. So we've got to show n0, half n0 and half-life t half. So if I sketch the graph, I know it's going to exhibit this sort of behaviour. Half n0 will be basically half the original amount. So it's going to be half n0, and half t half will be the time at which the number of atoms is a half. So that's it. Yeah, there's the initial amount, there's half the initial amount, and that's the time for it to be the half the initial amount. Part B, find the half-life of mathsium, this particle. Now half-life basically means the time it takes for it to be half its original value. So essentially what we need to find is t half. We need to find the value of t which is such that we get half the original value. So I'm going to use the formula given to me, and normally that's equal to n, but I want to make it equal to half n0 because I want to find the value of t which makes this equal to half the original value. I can cancel n0 on both sides, e to the minus kt equals a half. Remember, I want half-life, which is the time value. So I want t on its own. How do I do that? I can either ln both sides, or as you sort of seen before, you drop e as the base, have a half there, swap the half and have the minus kt there. Log base e half is just ln half minus kt, and t is obviously ln half divided by minus k, and k is 1.3 times 10 to the minus 2. So we're going to have ln, so you find the ln button here, ln 0.5 divided by minus 1.3 times 10 to the minus 2. And you get 53.31, which is roughly 53 years. Sorry, 53 hours. Okay, so it takes 53 hours to get to half its original amount. So let's just recap the skills needed to do well with natural logarithms. First thing is to don't panic, or not panic when you've got to deal with ln or e to the x. Just treat them as normal logarithms and normal exponentials. Okay, so if you have e to the x equals a number, turn it into a log form, log base e number equals x, rewrite it as ln. And if you've got ln x equals a number, then you rewrite it as log base e to the x, and you rewrite an exponential form. Okay, so there are some hard ones that we've been through, and we went through an applied example here, and that's the end of the video.